from the ASTM standards or BIS standards. They are recognizing or they are suggesting these standard values. If your material is harder, then you can take 0.2% of stain. If your material is less harder, you can take a 0.1% of stain value, or your material is softer, you can take 0.05% of stain value. You can use these stain percentage in your total stain. How it is? So the first step is, now see, this is I'm going to apply the offset method. Here I am. Here so I have got the stain values. Round about stain value is 0.8 stain values I have got here. Round about 60 kilonewton stress I have, because after conducting, so this is the stress 20, 30, 40, 50 and 60. Similarly here stain values are 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. These are my strain values, these are my stress values. But the case is, now I am not getting the yield point. Only I am getting the ultimate and fracture point. Now my aim is to find out the yield, definite yield of this particular material. Now I will come to here. First, what kind of material you are taken? You are taken copper material. Now you can check the copper whether it is hard, less hard, or soft. Among these three category, this copper is, which category will belongs? This copper belongs to which category? In all these three, among these three, the copper is belongs to which? Harder, less harder, or softer? This is your aim. This is your basic knowledge. You have to find out your material, or you have to know what kind of material I am selecting, whether I am selecting the harder material, less harder material, or softer material. That is your first job, is to know the type of material. Suppose copper is there, copper is a less harder material. I can take it as assume it is a less harder material. Okay, copper is a less harder material, then you can use the 0.1% of stain. Now I am coming here. Out of 0.8 is there. How much it is? A total stain is 0.8. 0.1% of total stain, how much it is? Point, or it can take it is 0.9 or 10 or 1. Total 1% of total stain is 1 is there. Now out of total stain, I can take 0.1%. Total 1 or can assume it is 10. Now out of this stain, whatever stain value will be a 0.9, stain value will be a 0.8, or stain value will be a 1, 2, 3. So like this will be a stain value. How much is there? Total 100 is there. Assume it is, if it is 100 is there, out of 100, you can take 1% of total stain. 1% of total stain. Total stain is 1 is there, 1% of total stain. I think 0.1 means, I think here I can get small point. So here I can get a stain value. If it is 0.2%, I can get here 1. 0.0, I can get here the 1 point. Total stain, 0.1% of total stain. 0.1% of total stain, maybe I can get here. 0.1, maybe 0.05, maybe I can get here. 0.2%, maybe I can get here. This one. Now you can leave these 2 points. Now we have taken the less harder material. So total 1% of total stain, approximately it will be here. Approximately it will be here. Right? Because total 1 is there, total 1% is there. In that 0.1% we have to take. So approximately it will be shown here. Now we are getting a point. You can name it as A, B, C. So that is left to you. Okay. Now you can hold this point, draw the straight line. Now you can hold this point, draw the straight line that must parallel to the curve. So like this. Yes, that must parallel to the this curve. This is exactly parallel to the, not like this. That must parallel to the curve. Not like this, not like this. Hope you understand. Don't draw like this. Don't draw like this. Don't draw like this. Don't draw like this. You have to make ensure that straight line should be parallel to the curve. Yes. Now parallel. Now it is parallel line. Just can hold this point to draw the straight line. Somewhere it intersects the curve. You just least bother about that, but your intensity to make ensure that straight line should be parallel to the curve. Somewhere it will intersect the graph. Yes. Later you can observe that first your duty is to maintain that my straight line should be parallel to the curve. Just you can hold it and you can try it. Somewhere it intersects the curve. Now again I got one more point. I can take it as a B. Yes, sir. Now here it will be a crosses. Correspondence to this, correspondence to this. How much it is? 50. Now how much it is? Stress value? Tell me. This is in between the 60 and 50. Maybe approximately how much stress value? Please.
55, sir.
55 you can take. It's very good. Now this is the stress line. Stress line. Now with correspondence to B value, it appears in between the 60 and 50. Approximately the stress, proof stress, proof yield stress or offset stress is equal to 55. Yes. Now you got the yield load. Yield load, how much it is? 55. Then you can come here. That is for this. Now this curve. Now I am ready for the solving the offset yield strength is equal to 55 divided by cross-sectional area. Yes, cross-sectional area of the sample. Now I am solving the yield strength of these kinds of the graphs also. Hope you understand this.
Yes, sir.
Huh?
Yes, sir.
Yes, not. Suppose if the graph will show like this, there is no problem, there is no difficulty. Directly, this will show the definite yield point. You can take directly, you can solve the yield strength, or you can simplify the yield strength or determine the yield strength. If the graph will be showing like this, then it is difficulty. In that cases, you have to note down your material, or you have to have the knowledge about your selecting material, whether it belongs to hard or soft or less hard. Based on that, the standard institutions are given the strain value. This is the given data. The standard values are given. Standard strain values are already given. We have to apply these standard values with respect to our material. If our material is hard, then we can take a 2% of your total strain. Total strain may be 200, 500, whatever it is. 2% of your total strain. Note down where it is exactly appears. Somewhere it will be appears because only 0.2% of total strain. Maybe it is approximately appears here, or if your material belongs to the less harder material, you can take a 1% of your total strain. Then you can note down it, or your material belongs to the softer material. You now in that cases you can take 0.05% of your total strain. Note down that point and hold that point to draw the straight line that must be parallel to the curve. Thereafter, that straight line will be intersecting the curve somewhere in the curve where it intersects exactly. You can note down that again we are got here the point. Then you note down so as I denoted as a B. You can take any alphabets. With respect to that point, here we can note down the stress. Now I am getting 55 stress. That's all the case divided by original cross-sectional area after sample. Now I got the definite yield point of this copper as well as yield strength of that particular material. Hope you understand this. Is it clear? Say yes or no. Is it clear?
Yes, sir.
Yes, sir.
Let's clear this.
Yes, sir.
Yes. Okay. Let's go on to next. Yes. Relationship between engineering strain and two strain. Now we have to establish the relationship between engineering strain and true strain. Yes. So how would establish the relationship between engineering strain and true strain? This is small kind of derivation which we can derive by establishing the relationship between engineering strain and true strain. Now, let's start. So, we know that engineering strain. What is engineering strain or normal strain? You can call it as a normal strain. Engineering strain is delta L divided by L naught or L original. Am I right? Yes, am I right? Hello. So how can I write this? Delta L means
Change in length.
change in length. Li. Li means instantaneous. L original divided by L original. Now just simplify. You can take common L naught. What will we get? Li by L naught minus 1. Yes. Okay. Now you can push this 1 to here. What happens? E plus 1 is equal to Li by L naught. Hope you understand this. we know that true strain is equal to ln of Li by L naught, summation of Li by L naught. That's what I can take it as a ln of Li by L naught. Sorry, Li by L naught. Because change in length, sum of all the change in length to the original length. We know that. So true strain is equal to ln of, because of summation of change in length to the original length. Sum of all the change in length to the original length, then I can take it as a ln. So in logarithmic, Li change in length to the original length. Hope you understand. Just I am writing like this. In previous I am writing this now. So first instantaneous length, second instantaneous length, third instantaneous length, and fourth instantaneous length. So that is what I am writing like this, ln of instantaneous length to the original length. That is what true strain definition. Now you can, so this is equation 1, this is equation 2. Now substitute the equation 1 into the equation 2. Equation 1 in equation 2. So true strain is equal to ln of, so Li by L naught, change in length to the original length. What it tells true strength? Change in length to the original length. What if, how many lengths are there? Just leave it. All the sum, all the change in length to the original length. That is also right. Now Li by L naught is equal to how much it is? E plus 1. Now I will take here strain plus 1. Now you can take this formula. True strain is equal to ln of strain plus 1. Engineering true strain is equal to ln of engineering strain plus 1. Very small relationship between the very small derivation. Now I'm not taking any external things. Here we know that more simple case it is. See what is it, how it is, the relationship between engineering strain and true strain. Okay. So now I am establishing the relationship between engineering strain and true strain. Though I know we know that engineering strain. What is engineering strain? Simple case. Just you can look at me. Simple, very simple it is. We know that engineering strain is equal to delta L by L. This delta L nothing but what? Change in length, I, instantaneous length, which means change in length, or if you use Li, you can take LF also. LF means final length. You can say it is a final length. That what I can say it is instantaneous length minus original length. Always instantaneous length means final length is more larger than the original length. So this delta L, just I am writing, just I am elaborating the delta L, change in length to the original length divided by original length. Now I am writing like this. Yes. Now I am coming here. L naught are common is there. Now I can take the common L naught. Now I'm taking the common. What we'll get? That is, you know about mathematics. Huh? So Li by L naught minus 1. After simplifying this, I will get like this. Just I can take the common of L naught like this. Common. So that is, you know. Now Li by L naught minus 1. Now next up, just I am pushing this minus 1 to left to right side. Now the negative sign is becomes positive. Now epsilon plus 1 or strain plus 1 is equal to Li by L naught. According to true strain, we know that summation of sum of all the incremental length divided by original length. This is what ln means. Now I'm taking it as a ln. While writing that summation, I'm taking that ln. Sum of all the incremental lengths divided by original length. This Li means sum of all incremental. If it is 3 or 4, Instantaneous length. Number 1, 2, 3, 4, 5. How many it is? That is what? Sum of all the summation of incremental length divided by original length. That is what? Li by L naught. Change in length to the original length. Ln of change in length to original length. Okay. Now this is equation 2 and this is equation 1. Now what I am doing? Just I am substituting the equation 1 into the equation 2. What is equation 2? True strain is equal to ln of Li by L naught. Already we got the value Li by L naught, or instantaneous time to the original length, is equal to F1 strain plus 1. Just this value I am substituting here. Instead of this, I am taking this. So now it becomes, hence the true strain is equal to a ln of strain plus 1. Which strain it is? It is engineering strain. True strain is equal to ln of engineering strain plus 1. Simple it is. And you can remember this formula for your future numericals. Next class, we will solve some numericals, very simple numericals based on this true stress and true strain concept. In that cases, this formula is important. You have to remember this formula for the future. Is it clear? Any doubts in this? Let's say yes or no, please. Is it clear or not?
Clear, sir.
Clear, sir.
Right. Simple it is. I know the engineering strain, just I'm simplifying this, just I'm substituting the value. ಹೋಗೇ ಬಿಡ್ತಲ್ರಿ ಇದು go to PTC space settings. Okay, tomorrow we will discuss the small numericals based on the true stress and true strain. Okay, now? Can you hear me? Yes? Right. Now I will leave the meeting. Next, I think mathematics is there. You just wait for the mathematics class. Madam, you come.